But there's something worse that can happen. Suppose the white dwarf is an old white dwarf. It went through its evolution quickly because it was more massive. And suppose that white dwarf is at about 1.3 or 1.35, something like that, solar masses. Now there is a limit to how massive you can make a white dwarf. If you make it more massive than 1.4 solar masses, that star will now collapse. The gravity is so strong it can actually overcome the Pauli exclusion principle, and it is now energetically favorable for the electrons to combine with the protons and make neutrons. When that process begins, the core begins to collapse. As the core begins to collapse, the carbon that's there is now becoming hot enough that it can fuse. And because it is held up by electron degeneracy pressure and not by gas pressure, as the carbon begins to fuse, that added energy is not going to expand the star and quench the reaction. Instead, it's going to get to a point where basically all the carbon blows up at once. That is not a nova, that is a supernova. So the so-called carbon bomb supernova is the way our textbook describes it. It's also called a type 1a supernova. And it's what happens when a white dwarf close to the 1.4 solar mass upper limit that electron degeneracy can support gets more mass and pushes it past that limit. The star collapses and then blows up. Type 1a supernovae are the most sought after objects by cosmology astronomers. And the reason is because they're all the same. They're all virtually the same. They're all 1.4 solar mass white dwarfs passing through this so-called Chandrasekhar limit, collapsing, triggering nuclear carbon fusion, and they all blow up at once. Their maximum luminosity is all the same. They're all at an absolute magnitude of negative 19.4. Now, it's not totally true that they're all literally identical because they can have slightly different chemical compositions. However, we've known for a long time now that there's a strong correlation between the chemical composition that we see in these supernova remnants and the rate at which the supernova declines in its brightness. So that's what you see up on top in this diagram. You see different chemical composition type 1 supernovae will decay at different rates. So the more massive ones will decay at a slower rate, and the less massive, the chemical compositions, and I forget at the moment whether these are the high metallicity ones or the low metallicity ones. But anyway, the giveaway is the rate of decline. So if astronomers can find these and measure their rate of decline, then they can calibrate them all and put them all onto a common light curve. So these are great standard candles, and they are the brightest things out there. They are the most luminous things except for galaxies themselves. And that means that we can see them all the way out to the edge of the observable universe. And it is by means of type 1a supernovae seen at all distances in the observable universe that we are able to measure not only the expansion of the universe, but the rate at which that expansion has been changing over the history of the universe. So without type 1a supernovae, we'd know a lot less cosmology than we do. Okay, what about high mass stars? So they have short lives, short and violent lives. They're the ones that can heat their cores all the way to the point of fusing up to and including iron. Since iron is the most tightly bound of all nuclei, the star is now in a big problem. Nothing can hold it up. You cannot get energy to hold you up further when you have an iron core. So here's what a 5 solar mass star will do. Starts here, hydrogen to helium burning, helium to carbon burning, comes up and goes back and forth here as it goes through more different kinds of burnings. A 10 solar mass star is going to do hydrogen to helium, helium to carbon, come up here, wander around, and then at some point it's going to go bloop and blow up. It is going to leave the HR diagram because it leaves, well, it leaves, it blows up. The star is gone. It becomes a supernova. In the process of getting there, it's going to, again, grow like an onion, like we talked about. The highest mass chemical elements, the iron, is in the center, and then silicon. Two silicons make an iron. You have magnesium and neon and so forth. You don't need to remember all these different chemicals. I do want you to remember iron is the most stable of all nuclei. I think that is important. There's that diagram again. So what about a 20 solar mass star? What is its life like? Well, now the hydrogen fusion doesn't take 10 billion years. It takes only 10 million years, 1/1000th as long. The helium fusion takes only 1,000,000 years. The carbon fusion only 300 years. The neon fusion lasts only 6 months. And silicon burning into iron only 3 days. Now here's a star about to go supernova. It's called Eta Carina. It's the most massive star that we know of, at least it was the last I checked. It's about 150 to 200 solar masses. Huge stellar winds are causing these nebulae surrounding it. Looking at it more closely, strong stellar wind. So now what happens at the end? Well, the iron core at the center gets larger and larger as more and more of the silicon burns to make iron. Again, eventually, because the iron cannot support itself by nuclear fusion, the weight is going to become so heavy that you energetically favor this sort of backwards weak force interaction where the protons will combine with the electrons and make a neutron. The normal thing is if you take a neutron and pull it out of an atom and leave it all by itself, they kind of go a little crazy. All by themselves, they can't handle it. And the neutron will literally just fly apart and become a proton and an electron and a neutrino. But here, we have it the very opposite of being all alone. It's now so crammed together with other stuff on top of it, it goes the opposite direction, combines and makes a neutron and a neutrino. We talked about neutrinos with the sun, these little teeny ghostly particles. They have no charge, so they don't interact electromagnetically. They are not baryons, so they don't interact by the strong force. They only feel the weak force and gravity, and because of that, they travel through almost everything with no trouble. However, the density in the centers of these stars is so high that even the neutrinos have a hard time getting out. So what happens is in just 0.2 of a second, the nuclear burning causes the core collapse, which raises the density and accelerates the reactions until the neutrinos are so densely confined that they help to blow apart the star. Now, all the details of supernovae type 2, which is what we're talking about now, are not really fully worked out because it's a very non-equilibrium process and takes big computers with lots and lots of physics, and it's just really hard. So, but we have some of the world's experts in doing that. Stan Woosley and his group up at UCSC and the people he's trained are some of the best people in the world for leading the understanding of these objects. So there you go. We've got a supernova type 2. Here's some interesting factoids. 99% of the energy release, the gravitational potential energy of the star, the collapse goes into neutrinos. 99% goes into neutrinos. Only 1% of that energy goes into the explosion. Again, the neutrinos mostly escape, but it's so dense that as much as 1%, which is actually a pretty vast amount for these things, will go into the explosion. Only 1/100th of that 1% goes into the visible light. And yet still, the light is bright enough to equal the entire galaxy. 100,000 million stars all together will not outshine the brilliance of that supernova. And that will last for weeks or even a month or two, outshining the entire galaxy it lives in. There's a hell of a lot of neutrinos, and neutrons flying around in this process. So protons and electrons combine to make neutrons. And those neutrons glom onto other elements, and they make heavy isotope versions of the elements that are heavier than iron, so-called R process elements. So R means rapid. You build up a whole lot of neutron-rich nuclei. And then through the weak force, then many of those will decay and become slightly less neutron-enriched, but different chemical elements. Too much nuclear physics, I don't want to burden you with all that. But here's another interesting fact, probably worth remembering, and that is that we have found through more detailed modeling that gold and platinum, the platinum elements, are made primarily not in supernovae explosions so much as in the combination of neutron stars, collisions of neutron stars. So how would you get that? Well, if you had two high-mass stars, each go supernova in a tight binary system, and somehow be so tight that they don't unbind by losing enough matter to fly apart, but they stay bound together now as two remnants, two neutron stars. Those neutron stars will spiral together and eventually combine in another kind of explosion, and out of that comes gold. So that's one reason why gold is so rare. You need a pretty unusual situation to favor the formation of gold. Okay, let's look at some supernova remnants. There's Cas A. This is the supernova that blew up in 1680, the last one that we know of that blew up in our galaxy. We're long overdue for these. Typically they go off about once a century. We've now gone 4 centuries without one. Now that's in a neighboring galaxy, or no, this is in our galaxy. This is Kepler's supernova. So this went off in 1604. This one's in a neighboring galaxy, the Large Magellanic Cloud. And so is this one. This one's in our galaxy, the Spaghetti Nebula. And the Veil Nebula is one of the nicer objects in the sky for astrophotography. My astrophotography students love to photograph this one. Part of the Veil Nebula. Very beautiful. Another part happens to be very close to a bright star, naked eye star in Cygnus. And then this is the Crab Nebula. So this is a supernova that went off 1,000 years ago and was recorded by the Anasazi Indians and also by, of course, the Europeans. And at the very center, that object right there, that is not a white dwarf. That is a neutron star. So this is even more extreme than white dwarfs. This is a star of pure neutrons. That's what's made at the center of the collapse of these high-mass stars. And it's only about the size of a city, about 10 miles across. Now, as pure neutrons, it's way more dense even than the white dwarf, which is made of tightly bound chemical elements, so mostly carbon. But this has even had the electron space moved out. This is nothing but neutrons. And so rather than several tons per cubic inch, this is several billion tons per cubic inch. So imagine an entire large mountain compressed down into, you know, a thimble. That's the kind of mass we're talking about. Cutaway of a neutron star. It's all neutrons. So they have the mass of the sun, yet they're only about the size of a city. Pretty amazing. they warp space pretty severely. The gravity is so strong, these things are almost black holes, but not quite. So a photon of light could easily lose a large fraction of its total energy just escaping the neutron star, maybe 10-15% of its energy. And so there's a strong gravitational redshift to that light. Okay, now, so these things are rotating. Stars, when they're normal, are rotating. High-mass stars might rotate once every 10 days or so. Now, what's going to happen, imagine a figure skater, when she brings her arms in, she spins faster. Well, now we've taken a star that was normally about 1,000,000 miles across, and now it's only 10 miles across. So we've compressed it by a factor of 100,000. So the rotation speed is going to go up by a huge amount, and so these things are now spinning at several to hundreds of times per second. Now that rapid spin of something this hot and still having charge in it, the neutrons have a magnetic moment to them even though they don't have a net charge, but they have a magnetic moment that they feel and can align themselves with and produce a magnetic field. They have actually a very strong magnetic field. And the magnetic field causes lines of magnetic force to go out along the north and south poles, and they act as out points for electrons that are out here spiraling in. They get in closer and closer, and then they actually get flung back out along the magnetic axis, as does light. So light itself will actually be channeled along these magnetic field lines because the electrons spiraling in will emit a certain kind of radiation called synchrotron radiation that is aligned with the magnetic field lines. And so the way to think of these things is they're like gigantic lighthouse beams. And those beams are aimed in a particular direction. And when those beams go across the direction to you here on Earth, then we see a flash of light. So if these things are spinning around at several times per second, then what you actually see is a flashing light that's flashing many times per second. And when we first discovered these back in 1968, they were labeled LGM1 and LGM2, and LGM stood for Little Green Men. It was a bit of a joke. They didn't really think they were extraterrestrial, but it was spooky how incredibly precise were the timings of these objects. So they're very, very, very good clocks. Okay, so we talked about that.